Welcome to EGR 445. In today's class, I plan on working out some helical gear problems, and later we'll talk about the bevel gears. So in the last class, we talked about the differences between the spur gear and the helical gear. So the idea in designing a helical gear is we convert this helical gear into an equivalent spur gear. And once the gear is designed into an equivalent spur gear, the usual gear design process works. Now, most importantly, if you have T as the number of teeth on the helical gear, those get transferred, or we change those to TEQ. And I gave the procedure, but just to remind ourselves, I will quickly write down the design procedure for the helical gear. TE, which is the equivalent teeth on helical gear, is T divided by cosine cube alpha, where T is the actual number of teeth on helical gear. Now, some of the important dimensions for the helical gear is addendum, is 0.8 times module, dedendum, one times module, minimum tooth depth, is equal to 1.8 times module, minimum clearance is 0.2 module, and the thickness of tooth is equal to 1.57 times module. Now, when we try to design, so step one, design based on beam strength So whenever we are designing a helical gear, they will give us the power and torque requirement. And from power and torque requirement, we have to find out the tangential load. So say if P is equal to power in watts, N is equal to speed in RPM, P is equal to 2 pi NT divided by 60. So alternatively, you can find out the value of WT as P divided by V, where V is the pitch line velocity, which is pi times dN by 60. Or you can find out WT from torque divided by the radius. Any of these equations would work. So looking at the first equation, which is the Lewis equation, that is given as WT is equal to sigma O times CV times B pi M y prime. Now, WT is a tangential load. So we got it from here. This is the tangential load. Then sigma O is the allowable stress. CV is equal to velocity factor. And this velocity factor depends upon the pitch line velocity. So CV is equal to 6 divided by 6 plus V when velocities are in between 5 to 10 meters per second. When the velocities are between 10 to 20, it is 15 divided by 15 plus V. When the velocities are greater than 20, we use its usual equation 0.75 divided by 0.75 plus square root of V. The velocities are greater than 20 meters per second. Now, next equation is B. B is the face width. And usually what we do is we express face width in terms of module. And sometimes these values are given to us. Sometimes the values are not given to us. So we can assume the module to be 12.5. So 12.5 to 20 M. Now, next part is Y prime, and Y prime is nothing but modified Lewis form factor. So this is the modified factor. What does it mean by modified factor? So first, you have to design a helical gear with T as number of teeth. So T is equal to number of teeth on helical gear. So from this T, you should find TE. It's T divided by cosine cube alpha. And use TE to find Y prime, which is Lewis form factor. In the case of spur gears, we will use just T, but in the case of helical gear, we are gonna use Y prime. The next step is we have to find out step 2. Find dynamic load. So dynamic load is WD, WT plus 21V B C cosine square alpha plus WT cosine alpha divided by 21V plus square root of BC cosine square alpha plus WT. And when we use this equation, value of C comes from the same table for Spur gears. So everything is the same. B is the face width, V is the pitch line velocity, but this alpha is nothing but the helix angle. Now, next step, which is step 3. In step 3, we have to find out the static tooth load. And static tooth load is WS is equal to sigma E B pi M Y prime, where sigma E is the endurance strength and this equation is exactly, so the helix angle for spur gear is 0. So for spur gear, helix angle is 0. What is not 0 is pressure angle. So there is a difference between the helix angle and the pressure angle. So spur gear, if you look at the way the spur gears are cut, they are parallel to axis. And if you look at the helical gear are cut at an angle. This angle is alpha. But please note, so if you want to verify, you can substitute alpha is equal to 0 in the equation for dynamic load, and you will get the same equation as the spur gear. Okay, next is the wear load. And the wear load is WW is equal to dP multiplied by B multiplied by Q multiplied by K cosine square alpha. And value of Q, value of K, it's same as spur gear. So when we try to work problem of helical gear, we'll be referring to the table in the spherical gear chapter. Now, if you want, you can use the mathematical expression to find K, which is sigma ES square sine phi n divided by 1.4, 1 divided by Young's modulus of Pinion, 1 plus 1 divided by Young's modulus of Gear. But the important thing to note here is phi n is called normal pressure angle. Now, what do we mean by normal pressure angle? It is important to note that the helical gear, basically you have a pressure angle and you have a pressure angle which is normal to the plane because of the helix angle. So normal pressure angle, which is tan phi n, this is important relationship that you should remember. Tan phi n is equal to tan phi cosine alpha. So please note, usually they will give you the value of phi, which is the pressure angle. But when we find the wear load, what we need to do is we need to find out the value of normal pressure angle. And once again, just like the spur gear, we want to make sure that our gear is safe. So what that means is you want to check if the WS, which is the static load, is greater. So I will write this here. This WS has to be greater than equal to WD, and WW should be greater than equal to WD. So what it means is the static strength and the wear strength of the gear is greater than the dynamic load. Now, I know I worked out a problem quickly, but let me work out one more problem. And in this problem, what I want to do is actually, I would like to solve the complete problem, starting from the gear design and moving on to the shaft design. And it would be instructive just for a second to understand what type of loads come on the helical gear. So if you look at the helical gear, this is how the gear is going to look like. And you are going to have a load which is coming like this. So what this means is, unlike spur gear, the load is at an angle. However, if you look at the value of WT, WT is in this direction. And that means you will have to use the cosine relationship to find out the actual forces in the normal plane. And let's work out the problem. And when we do the shaft design, I will show you how to find these values. So before I proceed, any questions at this point? Any question? Okay, let's work out a problem. So problem, design a pair of helical gear. And so we have to design a gear and a pinion. The speed of the driver gear is 1800, and the driven gear is 600 RPM. The helix angle, which is alpha is equal to 30 degrees, and the profile is 20 degrees full depth involute. So which means this gear has similar profile as that of 20-degree pressure angles per gear. Then the driver gear has number of teeth T is equal to 24, and both gears are made up with cast steel. So material cast steel, and allowable static stress, so sigma O is equal to 50 Newton per millimeter square, and face width is, so in this problem, face width is given as 4 times the circular pitch. 4 times circular pitch. So sometimes they can define the face width in terms of the circular pitch, and as you know, the circular pitch is nothing but pi times the module. So you can actually work the problem that way. Then overhang for each gear, this is important. Overhang for each gear is equal to 150 millimeters. Overhang for each gear is 150 millimeters. And the allowable shear stress for the shaft, so tau shaft is equal to 50 Newton per millimeter square. And the Lewis form factor, which is y prime, is given as 0.154 minus 0.912 divided by TE. And the velocity factor, CV, is given as 350 divided by 350 plus V. So in this problem, the velocity factor is given where they specifically say V is in meters per minute. And we can actually start with a design. So step one. So in this design, actually they try to simplify. They say design gears only for bending failure. Design gears only for bending failure. So this actually simplifies our work. So we start. So first and foremost, what we need to do is, since gear and pinion are made up with same material, and pinion made with same material, pinion is weaker. So we will design the pinion. So first, I'm going to find out the torque transmitted. Torque is P times 60 divided by 2 pi NP, where NP is the speed of the pinion. And it is something important to observe here. Speeds are 1800 and 600. So the gear ratio is 3. And the pinion speed is definitely higher than the gear speed. So we will say 22 10 to the power 3 60 times pi, which is 116.7 Newton meter, which is 116,700 Newton millimeter. The equivalent number of teeth, TE, is equal to number of teeth on pinion divided by cosine cube alpha, where T is 24 divided by cosine cube 30. So that gives me about 37. So if you want to find out the Lewis form factor, y prime, I should be using the number of teeth is equal to 37. So equation for Lewis form factor is 0.154 minus 0.912 divided by 37. That gives me 0.129. Now, next thing is we have to find out the module and other information. So let's start. If M is equal to module, PCD is equal to number of teeth times module. And a word of caution. So this is the actual number of teeth. So equivalent number of teeth, they come in the picture only when we are trying to find out the form factor. If we are not finding the Lewis form factor, we will work with the actual number of teeth. So tangential load, WT, is equal to torque divided by PCD by 2. So WT is equal to 2 times 11670 divided by m times 24, because number of teeth are given as 24. So we know diameter is equal to 24 m. Now with this, I should be able to find out V, which is pi dn by 60. If I want this in meters per second, if I want the peripheral velocity in meters per minute, I would just use pi times d times n meters per minute, where pi m is, so d is 24 times m and n is 1800, and that will give me answer 135 m meters per minute. So you need to divide this by 1000 because we are assuming module here in millimeter. So since module is assumed in millimeter, the diameter, this guy, will be in millimeter. So this needs to be divided by 1000 so that we get meters per minute. With this, we should be able to find out the velocity factor CV. For this particular problem, the velocity factor is explicitly given. If the velocity factor is given to us, we will use that factor. If the velocity factor is not given to us, then we will go with the usual equation, set of equations that we talked about. So CV is equal to 350 plus V. $350 plus 135 M. And we also know tangential load is sigma O multiplied by the velocity factor multiplied by B multiplied by pi multiplied by M multiplied by Y prime. So this equation now can be written as, one thing I want you to note is in this particular problem, B is equal to face width is given as 4 times PC, which is circular pitch. And circular pitch is nothing but pi times module. So B is equal to 4 pi m. So this equation we want to use. So sigma O is given as 50. CV is 350 divided by 350 plus 135 m. B is 4 times pi times m multiplied by pi multiplied by m multiplied by y prime. And to find y prime, we already looked at it. You have to use the equivalent number of teeth and use Lewis form factor equation 0.129. And this equation needs to be solved using some sort of trial and error or using calculator. So by trial and error, or if you have TI-84 calculator, it should be able to solve it. That should get you the value of M is equal to say 5.1 millimeter. So I would say module is equal to 6 millimeter. So once you have the module, gear is pretty much designed. So if module is equal to 6 millimeter, face width is equal to 4 times circular pitch, which is 4 times pi times module, is equal to 76 millimeter. Diameter is 24 times 6 is 144 millimeter, and number of teeth on gear is 24 multiplied by 3, because number of teeth on the pinion are 24. So, and ECD of the gear, this is the pinion, this is gear, is 72 times 6, it's 432 millimeter. Now the next part is the shaft design. So for shaft design, let's look at the problem once again. In this problem, they give us additional piece of information, and I want you to note this. The overhang for each gear is 150 millimeter. So in last lesson, we talked about various ways the gears can be mounted. So you could have gears that are simply supported. So gear and pinion, both of them are simply supported. You can have gear that is simply supported, and pinion that is cantilevered, or you could have gear and pinion both cantilevered. So this is simply supported, simply supported, simply supported cantilever, and cantilever, cantilever. So in this particular problem, they give us the distance to be 150. That is an additional piece of information that we can use. And what this means is this distance is 150. So this distance is 150 millimeter. So step 1, now please understand, in this problem, we are not finding out the wear load. So please note WD, W static, and WW. They are not found because the problem states the design gear only for bending failure. However, in general, when you are trying to design, you need to find out WW you need to find out WS and you need to find out WD. But in this problem, since the problem says that just design the gears based on the beam strength, we are not finding out WD, WS, and WW. But in all other cases, you have to find out these values and you have to show that WS is greater than equal to WD, WW is greater than equal to WD. This is required. Okay, let's look at the design of shaft. So first and foremost, since we have the values, tangential load, WT is 9725 divided by M. So this comes from the equation of torque divided by diameter by 2, which is 1621 newtons. Now, axial load is equal to WT times tan of alpha. And please note, this is the helix angle. And in this problem, helix angle is 30 degrees. So 1621 multiplied by tan 30. And that gives you 935 Newton. Now let's consider, since the overhang is 150, since the overhang is 150, and this is sort of the overhang is from the center of the bearing. This distance is 150, and then you have axial load. So let me show you how this load is going to look like. So essentially, when you translate, your load is going to look something like this. So the bending moment on the pinion shaft is going to be WT multiplied by overhang, which is 1621 multiplied by 150 Newton millimeter, and bending moment this is due to tangential load, and bending moment due to axial load is going to be WA dP by 2. So this may need little explanation. So please understand, this is WT, this is WA. If you look at the moment given by WT, this is WT times 150. But if you look at the moment given by WA, this WA is multiplying with the radius, which is dP by 2. And that is causing this moment. Now, it is important to observe that even though it may look like that these moments are counteracting with each other, actually they are not. They are, since WT and WA, they are perpendicular to each other. These two moments, which is the moment given by WT and the moment given by WA, are perpendicular to each other. So it is very important to note that when we do WA, which is 935 multiplied by 144 by 2 Newton millimeter due to WA. Please note these two moments are perpendicular to each other. Which means the resultant moment M is going to be the square root of bending moment due to WT and bending moment due to WA. So resultant moment is bending moment WT WA square. That gives you 252 Newton meter. We also know that there is a torque, which is T, and the torque is 116 Newton meter. So what this means is now we have the simultaneous action of moment and torque. That gives me T equivalent, which is square root of M square plus T square. And once I do this, I have 252 square plus 116 square, and that yields 277 Newton meter. And we can use the equation for torsion, which is tau is equal to T divided by J multiplied by R, where T is T equivalent and tau value is already given to us. So if you look at the problem, the shaft value, that stress for the shaft torsional stress is 50 is equal to 277 10 to the power 3 pi 532 d to the power 4 times t divided by 2. And from here, you should be able to get the value of shaft, which is approximately 35 millimeters. And that is how you will be able to solve the problem. What we have done is we have designed the pinion shaft. Pinion shaft. You have to repeat the same process and design the gear shaft. So it's exact same procedure. You have to find out the value of WA. The only difference here is here we used diameter of the pinion. But when we design the gear, we have to use the diameter of the gear. And what that means is the bending moment because of the axial load will go up. And when that goes up, you will have to follow the same procedure. Your equivalent torque TEQ will go up, which means the diameter of the gear shaft will be greater than the diameter of the pinion shaft. Once again, I have to caution you here that in this problem, we did not do this step. we did not do this step. And the only reason we did not do this, because in the problem, it said that don't check for wear or don't check for the static load. But otherwise, in all other cases, you will have to do this exercise. So you have to show that WS is greater than WD and WW is greater than WD. Okay. Any questions at this point? Any questions on the helical gear? Now, one thing I want to talk about is design of a gearbox. So for an example, if the problem says design housing or gearbox. Now, if the problem is going to ask you to design the housing or the gearbox, step one is to first draw the gear and the pinion. So what I'm going to do is I'm going to draw gear over here. I'm going to draw the pinion over here. And the next step is look at the configuration. For example, in this particular configuration, the gear and the pinion are cantilevered. And these distances are given to us. So this distance is given to us. Then what we should do is we should allow some dimension for the bearing. And actually those bearing dimensions are usually found out from the bearing design, but you can use a reasonable good bearing width. So, and usually depending upon the type of bearing you choose, you could use sliding contact bearing, you can use roller contact bearing, you can use taper roller bearing, you can use needle bearing, if you want to compensate for axial thrust, you can use thrust bearings. And let me quickly talk about how does sliding contact bearing work. So sliding contact bearing is nothing but a bushing. So this is the shaft, this is the bushing, and this is the case. So this is the sliding contact bearing. If you look at the roller contact bearing, what you have is you have an outer race, you have an inner race, and in between outer and inner race, you have rollers. You can also use ball bearings. So this is roller. So in the case of ball bearings, you have an inner race, you have an outer race, and you have the ball bearings. And there is something called as the cage that holds. So you have balls and cage. And you have inner race, you have outer race, and you can choose depending upon the application what type of bearing to be used. However, in this particular case, I have to emphasize you are using a helical gear. Since we are using a helical gear, what that means is you are going to have an axial thrust. You are going to have an axial thrust. So simple ball bearing cannot take the axial thrust. So you need to use sort of a combination bearing, or you have to use the ball bearing along with some sort of thrust bearing, or you can use a taper roller bearing. So what is the difference between the roller bearing and the taper roller bearing? In the taper roller bearing, what you have is you have rollers. They are actually tapering. So you have inner race, you have outer race. Again, you have the cage that holds these rollers together. But the biggest advantage of taper roller bearing is, as you can see, taper roller bearing can take thrust loads. So the inner cage or the inner race and outer race and the cage, they do not separate out when you have a thrust load. So typically in the helical gear, I have seen using taper roller bearings. So you can assume taper roller bearings here. So I'm going to assume taper roller bearing, and then I'm going to construct a housing around it. So I'm going to construct the housing around it. And this is purely from the geometry point of view. We are not doing any of the stress calculations. The only calculation that may be performed is the heat dissipation capacity. And I will talk about it in just a second. So this is how the housing is going to look like. So the only calculation that could be performed, but not really required, is the heat dissipation capacity of the housing. So heat dissipation capacity. So believe it or not, whenever you have a gear drive is not 100% efficient. It's very efficient, but it's not 100%. So what's going to happen is you are going to have some power loss. So power loss is equal to 1 minus efficiency of the gear train multiplied by power transmitted. And this power loss is converted to heat. And what happens to this heat? If you look at the casing, usually there is some type of lubrication, some oil that is being circulated. Many a times the gear run in oil, or many a times you have an oil reservoir And because, so you can have an oil reservoir, and because of, since the gear is rotating through the oil reservoir, the oil gets splashed and the heat is dissipated. And what happens is this oil heats up, comes in contact with the housing, and from housing, the heat is actually radiated, or we can use forced convection or free convection. So you have heat that is sent out to atmosphere. So to do that, what we do is we say K times area of housing multiplied by delta T. And this is heat dissipation coefficient. And many a times, if you are using free convection, so if you are using free convection, use HF. And if you are using forced convection, use HF prime. So what do we mean by free convection and forced convection? So you have the housing just like this. The gear train is inside, it's heating up. The housing heats up, the temperature increases, and there is no fan or there is no forced air circulation, and heat on its own gets dissipated because the air comes in contact with the hot surface. It takes some energy from the hot surface. The energy of the air and the velocity of the air increases, and that air dissipates the heat. Alternatively, what you can do is you can add fins. If the area is not sufficient, then you can add fins to it so that the heat dissipation is better. And when you study heat transfer, fins are these small projections that improve the amount of heat transfer from the surface. Now, many a times what you can do is you can have an external fan. You can have an external fan that actually increases the airflow. And in certain cases, what you do is you extend this shaft outside and add a fan over here. So the gearbox, and then clearly you need to add the cage around it. So fan and cage. So many a times what happens is, since you are using this gearbox for some sort of power transmission, you can just add a fan to the gearbox, and that helps to cool down the gearbox. The also other important thing is selection of oil. So oil selection is also important. So lubrication, oil selection. So if you look at the car engine oil, there are different grades: SAE 5, SAE 20, 10W, SAE 5, 20W. So there is an SAE standard for viscosity of oil. For viscosity. And then you need to make sure that the oil is able to withstand the minimum temperature and the maximum temperature without losing its properties. Because here is something that is possible, that you select an oil and then your gearbox is running in a cold weather. And what happens is, if the oil is not able to maintain its viscosity, then it may become more viscous. That will actually drag the gearbox, and that will increase the amount of losses. So, or if the gearbox heats up significantly, then what would happen is the viscosity of the oil would drop down, the lubrication capability of oil would drop down. Oil will not stick to the surface to dissipate the heat, and there will be some sort of lubrication failure. So you want to make sure that you are selecting the oil that can behave satisfactorily within these limits. And many a times these oils, uh, when you design, you have to see whether you are designing the gearbox so that the oil needs to be periodically replaced or that gearbox is sealed. So this is something like automotive transmission. Some transmissions are sealed, which means the oil that is used for lubrication will last for the lifetime of the transmission. Some gear transmissions are oils are not sealed, but the oil is circulated through a cooler, which means the oil on its own uh, cannot dissipate the heat directly because there is not enough area. So what you do is you have this gearbox, and from this gearbox you have a pump. That pump actually pumps the oil through this radiator, and the cooled oil again goes back to the gearbox. So there is a pump, the pump, this is the radiator, and you have the oil that is continuously circulated from the gearbox to the radiator. And this type of arrangement is preferred when for some reason this entire gearbox is enclosed and you have no airflow. So there is no airflow. This is no airflow, which means there is no way you can cool the housing with external forced air. So you have no other choice than to uh, run the oil to a radiator and cool it. If you look at your cars, many of the cars, if you look at your radiators that are used to cool the coolant, what you will notice, usually you have a radiator cap, then you will have on top, there is one hose, on the bottom, there is one hose, depending upon how your radiator is designed. And then here, there is another small, teeny tiny radiator. And this radiator is specifically for the transmission fluid cooling. So you have this water that goes around here. Now what happens is this water is circulated around the fins of the transmission cooler, and that heat is dissipated. So this is the radiator for engine coolant, and you have the cooler. This is again small radiator or called oil cooler for transmission oil. And with this, typically the gears are lubricated. And this is an important piece of information that you should keep in mind. And make sure that the lubrication properties are sufficient, and that is the reason why there is an oil change interval. So what happens is, just if you think about the oil changes, the oil is continuously circulated inside your engine that has lots of gears and lots of moving parts. And then what happens is that oil is cooling. Not only that, there is some micro abrasion taking place. So oil is washing away that micro debris, and that oil, it's filtered and then fed back again. But over the period of time, say 3,000 miles, 4,000 miles, the amount of debris increases. The filter loses its filtering capacity, and oil doesn't get purified or filtered to the extent that we really want to. The oil starts degrading. Oil cannot carry out the sufficient amount of heat, and you will notice that oil starts smelling burnt. It becomes black, and you will notice that the engine performance deteriorates. So that's why the automotive manufacturers specify a certain duration in which the oil has to be changed, just to make sure that the oil is maintained at its peak operating performance. So these are the important notes on the helical gear. What I'm going to do is we are going to stop here for 15 minutes. I will come back and then we will discuss the bevel gears. So the class will continue after the break of 15 minutes. But before I give you a break, any questions? Okay, and we'll stop here for 15 minutes and we will be back at about 7:30. Okay, design of bevel gears. Now, what is the difference between the spur gear or the helical gear versus the bevel gear? So if you look at the spur gear or helical gear, the shafts are parallel to each other. So the shaft of the spur gear pair, so they are parallel and they are non-intersecting. On the other hand, if you look at the bevel gear, typically the bevel gear, you can have that two gears perpendicular to each other, 90 degrees to each other. Or the bevel gears can be at different angles. So you can, so nobody has prevented us from having a bevel gear which is not at 90 degrees. So the angle between the shafts can be 90 degrees or can be different. Now, it's important to observe that the bevel gears are used if the both the gears have the same diameter. So which means the only purpose is that we want the direction of power transmission to be changed. So if both the gears are perpendicular to each other and then the diameters are the same, they are called meter gears. or the pair of bevel gears. Now, bevel gears are typically found out in automotive transmissions. So for example, if you have a rear wheel drive, you are gonna have a differential. So you have the power coming from the prop shaft, and you have this differential assembly that is attached to the axle. And there are different configurations possible. It could be limited slip or additional configuration that would allow the differential to work effectively. Now, what are the major terms in the bevel gears? So let's see how do these bevel gears look like. So what you have is, you have one gear, and you have other gear, and if you look at the way the gears are, the shafts, the center lines of the shafts in this configuration are intersecting at this point. And this point is called as point O. So point O is where these shafts are intersecting. If you look at the way the gears are constructed, it is similar to having two cones. So if you think about it, it's like you have a cone 1 and cone 2 corresponding to each gear. So what I'm gonna do is, there is something called as the front cone, which is shown over here. And there is something called as the back cone, which I'm showing over here. This is the back cone. So this is the gear. This is the pinion. And so there is something called as the gear angle. And so this angle I'm gonna call as theta G, and I'm gonna call this angle theta P. So theta P plus theta G is equal to 90 degrees in this case. And there is something called as the cone distance. So this is cone distance. This is cone center. Then this is the diameter of the pinion. This is the diameter of the gear. And then just like the spur and helical gear, you're gonna have the addendum, dedendum, and all other parameters. But the important thing here is you have a base cone and the gear is formed on that cone. So some of the important terms in the bevel gears, and these are important corresponding to bevel gears. You won't see these terms uh, like pitch cone, cone center, etc. for the spur or helical gears because the shafts are parallel. So pitch cone is the cone that contains the teeth. So cone containing teeth. So when we look at the bevel gear, to cut a bevel gear, you have to start with a cone, and then basically the cutter will continuously cut the teeth on the bevel gear's blank. And it's an interesting machine. So I would encourage you to go on to YouTube and watch bevel gear cutting machine. And it's very informative at how the bevel gears are cut. The next thing is the cone center, which is the apex of cone. Then you have something called as the pitch angle, which is the angle made by the pitch line. So you have pitch angle, which is angle made by pitch line. Then you have something called as the cone distance, and that is important. Cone distance is OP is equal to pitch radius divided by sine theta p. So I just want to talk about what is this pitch radius. So if you were to look at the gears, two bevel gears that are meshing, and if you were to look at the center lines of these two shafts, so this is the gear, this is the pinion. So this distance, this point, is called as point P. This angle is theta G, and this distance is RG. Similarly, if you look at the pinion, this is RP, and this is theta P. Now, one thing that we need to take into account is if you look at the distance OP, if you look at the distance OP, whether you consider OP on the pinion or whether you consider OP on the gear, it is the same. So if you look at OP on pinion is equal to R pinion divided by sine of theta P. If you were to look at OP on the gear, which is equal to R gear divided by sine theta G. And this is an important observation because from this observation, we can derive something like sine of theta G divided by sine of theta P is equal to Rg divided by Rp. Rg is the radius of gear. This is the radius of pinion. And this is nothing but the gear ratio. Is equal to R, also called as the velocity ratio. So this information will be used when we work out the problems. The next piece of information is something called as the addendum angle. Now, addendum angle is nothing but the angle that is subtended by the addendum of the tooth to the cone center. So just like the spur gear, where we have addendum, dedendum, and total tool depth is addendum plus dedendum. So addendum angle is given as alpha, which is nothing but tan inverse of A divided by OP, where A is the addendum and OP is nothing but the cone distance. Similar to addendum angle, we have a dedendum angle, which is D is dedendum. And then you have something called as the face angle, and the face angle is the angle subtended by the face of the tooth to the cone center. At cone center. Then you will have the same stuff, back cone distance, mounting height, the pitch diameter. These parameters are used when we actually design the gear. But just like spur gear and helical gear, the most important parameter in the case of bevel gear is again the module. So always keep in mind that addendum angle, dedendum angle, they are important, but the most important relationship for the bevel gear is this relationship. And then there is an alternate way that this relationship can be written, but it's not really needed. So what you can do is, let me take two cases just for the discussion. Case one, when the bevel gears are at 90 degrees. In that case, you can use the relationship theta p is equal to tan inverse of 1 divided by velocity ratio or r, and theta g is equal to tan inverse of velocity ratio. The other relationship that we know, theta p plus theta g is equal to 90 degrees, which means once you find theta p or theta g, you should be able to get the answer. Case 2, when the bevel gears are not at 90 degrees. So bevel gear are not at 90 degrees. The alternate relationship that is given as theta p is equal to tan inverse of sine theta s divided by velocity ratio plus cosine of theta s. And theta p2 or theta g is equal to tan inverse or once you find so total angle minus theta p. So that is something that you should keep in mind. And the other way to derive the same equation, is something like this. So sine theta p2 divided by sine theta p1 is equal to d. And this is the same relationship. Instead of r, we are going to multiply that by 2. So this becomes d. So let me just make this g dg p is dp, and the second relationship is theta s is equal to theta g plus theta p. So if you have these two relationships, then you should be able to find out these angles. And I will work out the problem wherein we will discuss how to find out those angles. Now, important proportions for the bevel gear. So proportions for bevel gears. So first one is addendum. Addendum is given as A is equal to 1 times module. Next one, dedendum is equal to D is equal to 1.2 times module. Clearance is equal to 0.2 m. Working depth is equal to 2 times m. Thickness is equal to 1.5 m. and M is equal to mod G. Now, one thing that I have to specify here is determination of equivalent number of teeth. So determination of equivalent number of teeth for bevel gear is slightly different than the helical gear. Now, and here is the argument. So for an example, if you look at the involute profile for the spur gear, if you look at a spur gear, and this is how the spur gear looks like. This is the involute profile for the spur gear. This profile, and when I say the gear profile, I mean by this profile, this involute can be generated by a line or a plane rolling on the circle. So this profile that is traced is involute. But however, in the case of bevel gear, so similar section would lie on a surface of a sphere. So this is important. For spur gear, your rolling plane rolls on cylinder. But think about the bevel gear. Bevel gear is in 3 dimensions. So for the bevel gear, the plane rolls on sphere. And that is very important. But if you look at this typical geometry, this is a 3-dimensional geometry. It is not possible to completely express this 3D geometry onto a 2D plane. So what we do is we use something called as the Treadgold approximation. To represent 3D bevel gear geometry to 2D plane. And what it does, it depends upon the fact that if you have a tangent or a cone that is rolling tangentially on the sphere, then it will be the approximate spherical trace on the pitch point. So without going in much detail, what it means is if you think about the bevel gear, if you think about that you have a cone, so you have a cone and that is rolling on the sphere. So you have this cone and this rolling on the sphere, you can actually have sort of a projected gear on the backside. So this is, if this is the pitch point, this is the pitch point P, then you have an approximate projected gear. Now, what is the implementation or what is the application of this? The application of this is very simple. So if you want to find out the equivalent number of teeth for the bevel gear, you want to find equivalent number of teeth for the bevel gear, and you have actual number of teeth for the bevel gear, you divide that by cosine of the pitch cone. where TA is the actual number of teeth, and theta P is the pitch cone angle. So that is what it means. So you have to use Treadgold's approximation to convert a three-dimensional bevel gear geometry onto a two-dimensional, some sort of a two-dimensional equivalent system. And that gives you an equivalent number of teeth. And that is nothing but the actual number of teeth, that is TA, divided by cosine of the pitch cone angle. And so if you compare this with the helical gear design, in the helical gear design, we also did the same thing, except when we were trying to find out the equivalent number of teeth, we used cosine cube alpha. So here, instead of using cosine value, cosine cube, we are just going to use cosine of the pitch cone angle. So now, how do we go further in the bevel gear design? Bevel gear design is similar to the helical gear design and the spur gear design with some small changes. So let me sort of give you the procedure for bevel gear design. So bevel gear design steps. Step 1 is beam strength. And we find out the tangential load WT and tangential load, same equation, sigma naught multiplied by the velocity factor multiplied by B times M multiplied by Y prime. But here there is one more term comes in the picture, which is L minus B divided by L. So if you look at the previous examples for the helical gear design or the spur gear design, we did not have this additional term L minus B divided by L. So this term is present because of the cone. Since the bevel gear is cut on the cone, we have this term. Y prime is the Lewis form factor, which is based on the equivalent number of teeth. Other than that, all the terms are exactly the same. Sigma O is allowable stress. CV is equal to velocity factor. B is equal to face width. M is equal to module. Y prime is Lewis factor. And L is the slant height. That slant height is nothing but the radius of pinion square plus radius of gear square, because we are going to use the Pythagorean theorem, and that gives me the value of L. So where RP, radius of pinion bevel, RG is radius of gear bevel. And this is also called as the bevel factor. So step 2, but one thing I just have to tell you that face width for the bevel gear B is usually 6.3 to 9.5 times module. So the face width is between 6.3 to 9.5 times module. And L by B ratio should be less than or equal to 3. This is just for the safety purposes. And number of teeth on the pinion. So number of teeth on pinion should not be less than 48 divided by square root of 1 plus velocity ratio square. And some of you may just remember this is something similar to the number of teeth, minimum number of teeth that are needed to find out the for spur gear to avoid interference. The next part is step 2. Find dynamic load WD, and equation for dynamic load it's same as spur gear. And we would just use the same equation. A quick recap, we looked at the equation for the helical gear. So if you substitute value of alpha is equal to 0 in the dynamic load equation, you will get the equation for the spur gear, and that is the same equation that we are going to use. Step 3, is we have to find out static load, which is Ws is equal to sigma E B pi M Y prime and the bevel factor. So the only difference between step 3 and step 1 is we are using the value of sigma E, which is the endurance strength. This is the endurance limit. Then step 5, I'm sorry, this is step, what did I, step 2, yeah, step 3 and step 4. We have to find out the wear load, is equal to WW is equal to dP V times Q K divided by cosine of theta P1, where theta P1 is the semicone angle and Q is 2 times equivalent number of teeth divided by TEP plus TEG. So this is very important that I want you to note. This is equivalent number of teeth on gear, which is TG divided by cosine of theta G. And TEP is the equivalent number of teeth on pinion, TP divided by cosine theta P. So that is the difference that you want to talk about it or take into account when you actually solve for the problem. Wear load is always calculated based on pinion. So dP is the diameter of the pinion, and the K factor is found similar to the Spur gear. So any questions on the design process? So as you can observe that the design process for the bevel gear is derived from the Spur gear design. Now the next part is I just want to give you some outline or hints for the shaft design for the bevel gear. So shaft design for bevel gears. So first and foremost, we need to find out value of WT, which is tangential load. And tangential load can be found out either from torque or it can be found out from the pitch line velocity. So P is equal to power and V is equal to pi times T times N divided by 60. Now what we need to do is, once we find out value of WT, we need to find out the axial and radial forces for the pinion. And so the reason for that is, if you think about the bevel gear, let's consider the bevel gear, which is like this. You have a tangential load. A tangential load is going to give you an axial load and you are going to get a radial load. So this is the front view. And if you look at the top view, you are going to see a tangential load. So you will have WR and you'll have WA. So WT is a tangential load. WA is the axial load and WR is the radial load. So again, depending upon how the gear is constructed, depending upon how the gear is supported, some of this process could be slightly different. But what we need to do is, at the end of the day, we have to find out the moments given by these individual loads, and then we have to find out. So just to give you an idea, first we will find out WT. From WT, we will get WA. Once we find WA, please note WA is acting at this distance, which is the radius of the pinion. So it's gonna give you a moment. So M due to WA, moment due to WA. Then you have WR. So M WR is moment due to WR. And then what we need to do is we have to find out the resultant moment. So this resultant moment is the vector sum of these different moments. So it is important to observe that the moment given by WR is in this direction. So moment given by WA is in this direction. And if you look at the moment that is given by WT is perpendicular to the other moment. So what you need to do is you will have to find out the equivalent moment. So I'm going to call this M, and I'm going to call this M due to WT. So I will call it MWT, moment due to WT. So you have to find out the resultant moment. And I will work out a problem wherein what dimension is L? Dimension L is the semicone. So L is equal to R pinion square plus R gear square root. If you look at, and that is actually called as the slant height. So basically this distance is L. So if you look at, this is the radius of the pinion, the radius of the gear, and this distance is L. Okay, then we had to find out the torque, which is already known. And then we have to find out TEQ, which is square root of M square plus T square. And then use the equation tau is equal to T divided by J multiplied by R. And from here, you can find out the diameter of shaft. Okay, so these are the steps for the bevel gear design. And let me work out a few problems. So let's start with a fairly straightforward and simple problem. Design bevel gear for power requirement P equal to 35 kilowatts, speed 1200 RPM, and the driven gear is running at 780 RPM. So this is pinion and this is gear. So the bevel gears are at 90 degrees. So the gears at 90 degrees. And the pinion, number of teeth on pinion are 30. Pressure angle is equal to 14.5. And the dynamic stress value of sigma W for this particular problem, they have already given an equation 140 280 divided by 280 plus V. So in this case, the equation for dynamic stress is given. If it is not given, then we have to use the equation for the spur gear. The V is the pitch line velocity in meters per second, and the form factor, which is Y, is given as 0.124 minus 0.686 divided by T. Where TE is the equivalent number of teeth. The face width is equal to 1/4 times the slant height L. And we just talked about what the slant height is. So we have to find out for the pinion, the module, and all other dimensions. So design the pinion. So good news here is we can assume pinion and gear are of same material. So pinion is weaker, and we'll design pinion. So in this particular case, since the gear and the pinion, both of them are made up with same material, gear is going to be stronger than pinion. So we will say M is equal to module, and face width. So here, please note this additional information that is given to us. Face width is B. B is equal to L divided by 4. DP is the diameter of pinion, and velocity ratio is equal to speed of the pinion divided by the speed of the gear. It is equal to 1200 divided by 780. And the number of teeth on the gear, TG, is equal to the gear ratio multiplied by 1.53 multiplied by 30. So it's approximately 46. So what we are going to do is we are going to use this information to find the semicone angle. So theta P is tan inverse of 1 divided by velocity ratio, which is tan inverse 1.53 is equal to 33 degrees. And theta gear, since they are at 90 degrees, 90 minus 33, 57 degrees. So with this information, we should be able to find out the formative number of teeth for the pinion and gear, or the equivalent number of teeth for pinion is equal to number of teeth on pinion divided by cosine of 33. TE for gear is equal to number of teeth on gear divided by cosine of 57. So 30 divided by cosine of 33, 46 cosine of 57. So this gives me 35.8 and this gives me 84.4. So what we can do is we can find out the value of y prime, which is 0.124 minus 0.686 divided by 35.8. 0.105. And then what we need to do is we need to look back in the spur gear design and select the appropriate material. So I'm going to select steel, alloy steel for gear and pinion, alloy steel for gear and pinion. And then value of sigma O is 140 megapascals, which is 140 Newton per millimeter square. So first we need to find out the value of torque. Torque is equal to P divided by 2 pi n by 60. And we are going to design the pinion. So I'm going to use the speed of the pinion. Then I get the tangential load, WT is equal to T divided by the radius of the pinion. And since we don't know the radius of the pinion, but we know radius of the pinion, it's diameter of the pinion divided by 2. Diameter of the pinion is module multiplied by number of teeth on pinion divided by 2. But please note, this is actual number of teeth. these are not equal number of teeth. These are the actual number of teeth. So that gives me 2 TP so sorry. So this is going to be 2 times 278 3 divided by m multiplied by 30. That gives me 18,575 Newton divided by m. So now we know the value of Wt. Now we need to find out the velocity factor. So pitch line velocity V is equal to pi times d times n by 60. But please note, in this particular problem, if you look at the problem here, the pitch line velocity, actually I made a mistake, it's not meter per second, it's meter per minute. So please make a note. So pitch line velocity V is in meters per minute. So we won't have this term over here. So V is equal to pi times m multiplied by number of teeth on pinion multiplied by the speed of the pinion. That gives me 113 m meters per minute. So this is the pitch line velocity. With this pitch line velocity, I should be able to find out the value of working stress, which is 140, 280 divided by 280 plus P. And once I do that, I have an equation, 280 divided by 280 plus 113 times m multiplied by 140 Newton per millimeter square. And now with this, we are able to solve for the problem, except we need to know what is the value of L, and L is nothing but the square of RP RG square root, and RP is module number of teeth for the pinion divided by 2 square plus M TG divided by 2 square root. And when you substitute these values in the equation, so I'll give you the equation, WT is equal to sigma OP times CV B times pi times M Y prime, and the bevel factor, which is L minus B divided by L. So this equation reduces to, I'm going to call this sigma W. And unlike the previous problems, in here, the value of sigma W is directly given. So that is the slight difference between the problem earlier and the problem here. Alternatively, what you can do is you can find sigma W as sigma O times CV, and sigma O you can consider to be, say, 140. Sigma V you can assume something like 6 divided by 6 plus V, and then substitute this value here. So both methods are correct. So you can actually use the equation that is given in this problem just for this particular problem, or you can use the standard generic procedure, and that way now you have terms on the left hand side and terms on the right hand side that are expressed in terms of M. So you have 18,500 divided by M, 140, 280 divided by 280 plus 113 M multiplied by B, which is nothing but 6.88 M multiplied by pi multiplied by M. And please note, we already found out the value of Y prime, which is 0.105 multiplied by L, which is 20. So once you substitute the values in here, you will get the value 27.5 M minus B, which is 6.88 M divided by 27.5 M. So this equation that looks complicated, but the only unknown is M. So you have to solve this equation using trial and error, or you can use the calculator TI-86 or 84, and you should be able to find out the value of M. And the value of M in this case is about 7.1 millimeters. So I would approximate that to 8 millimeter. With that, I should be able to find out the value of the face width B, which is face width is equal to 6.88 times M, that is 55 millimeter. And the next part is we can find out the value of addendum, which is 8 millimeter, which is then you can find out the value of addendum, which is 1.2 times 8. And then you can find out the slant height, which is L, which is given as 27.5 M, which is about 220 millimeter. So this is the basic design. The next step is we have to find out, the next steps are, we have to find out the value of the wear load, and we have to find out the value of the static load. So to find out the value of static load, we have to use the equation sigma E, and please note that equation is given here. Sigma E, sorry. So we have to find the dynamic load. So we have to find dynamic load. WD is equal to WT plus. At this point, we have to go back to the chapter on spur gear, because the dynamic load equation for the bevel gear is same as the dynamic load equation for the spur gear. So quickly go back and look at that equation. and I will give you that equation. That equation is given as WT plus 21V BC plus WT divided by 21V plus square root of BC plus WT. And you will find the value of C from table 28.5. And then once you find the value of WT, B, the value of face width is already known. Value of V is already known. So please note the velocity is given as 113 times module. So V 3 times module. But please notice that this velocity has to be in meters second. Make sure that this velocity is in meters second. Next step, step 3, is find static load. And the equation for static load is given to you. So here is the equation for static load. Sigma E B pi M. So WS is equal to sigma E pi times B times M L minus B divided by L Y prime. So, and the last step is find wear load, which is WD, and WD equation is dPBQ divided by cosine theta P1. dPBQ K divided by cosine theta P. But one thing that you should keep in mind is Q is given as in terms of equivalent number of teeth. Q is 2EQ divided by EP plus TEG. And then check whether WD, so this is wear load, WD is less than equal to WS and WD is less than equal to WW. And actually I'm running out of time, but I will work out another bevel gear design problem, including the shaft design, in next class. So at this point, if there are any questions, I would be happy to answer.